some of the forces. Electrostatic force, magnetic force, gravitational force. Electrostatic force and magnetic force are both polarized. The gravitational force is unidirectional, it pulls. All it does is suck. Gravity sucks. And the older you get, the more it sucks. Okay, with respect to matter, gravitational electrostatic force always exists. They're always doing their thing. Magnetic force, it technically exists in all the electrons. However, because the electrons are always doing, running around in a non-coordinated manner, the resultant magnetic forces are all canceling each other. Okay? So if we can get all the electrons in a material to behave the same way, then instead of canceling each other, the magnetic forces will all work adding to each other, and the property of the material will become magnetic. Now, it turns out that anything can be magnetized. Any form of matter can be magnetized. All but a few forms of matter will very quickly lose their magnetism. All elements and all compounds lose their magnetism at different rates. So if I use various different forms of radiation reflection like radar or X-rays or something else like that, and I supermagnetize something, an object, and then start doing this imaging very, very quickly as the different materials, different elements are demagnetizing, I'll get a really good image of all the different elements in that object. We call that magnetic resonance imaging, or MRI. That's what they're doing. They're magnetizing every atom in your body, right? Or in the area that they're examining, and then they're hitting you with, not with an X-ray, but with it's very much like a radar pulse, only very, very quickly, multiple times per millisecond. And as the hydrogen, oxygen, hydrocarbon, whatever different tissues degrade in their magnetism, their signature changes, but that allows the imaging to say, okay, that was brain tissue, that was bone tissue, ear tissue, nose tissue, or whatever the different kinds of tissues are, and what it creates is a three-dimensional model of data contained in a computer. Then the doctor goes, all right, in this three-dimensional model, take a slice of that data and show me what it looks like here, or at this angle, or at that oblique angle. And so they then go through and come up with a bunch of pictures. That's all because anything can be magnetized. There's about 4 or 5 metals, iron, cobalt, nickel, and a couple others, that they'll retain their magnetism for quite a period of time. Iron will retain its magnetism for a very long period of time. It does degrade, though. And in fact, the only thing that keeps the Earth magnetized, it would have degraded over many, many years, but unfortunately there's this thing called the sun that keeps magnetizing it. So it stays magnetized, very magnetized, actually, as planets go. Okay, so this polarization not only exists between the particles, but it also exists between the lines of force that are created by this behavior. It's a little bit easier to see in magnetism, and the next slide will probably show you some pictures of those lines of force. But a way of describing it is to say, if I've got 2 objects repelling from each other and a string between them, as they're trying to pull apart, the string is going to keep them together, and that'll form one line of force. But there'll also be a bunch of other lines of force adjacent to that line of force. The lines of force, if they're going the same direction, don't like each other. Okay? So they have a tendency to spread out. Okay? When they're going opposite direction, they have a tendency to compress together. As well, here, when I've got two objects of the same polarity, as they start coming together, all the lines of force start trying to distort, and they don't like sitting next to each other. So that's a part of what separates or pushes, repels the two like particles, in this case, protons. So like attract or repel, opposites attract. We named the proton positive as a force and the electron negative as a force. The amount of pull that the electron has for the proton is the same amount of pull that the proton has for the electron, back and forth. So they both are pulling equal amount, even though this one is 1,830 times bigger than the little one. Okay? So needless to say, 1,830 times bigger, this one little bitty, which is going to move towards the other. The electron is going to move towards the proton. Only the issue is electrons like to move at the speed of light. So they're going so fast. Now, why do they like to move at the speed of light? I don't know. I don't have that answer. But they do. They like to move at the speed of light. They keep on moving at the speed of light. So they're not going to stay there long. They're going to go around, and they're going to get stuck in an orbit with that static force holding them there, and then buzzing along at the speed of light, traveling around. So these lines of force, we say they orient in direction because we've got to have some orientation so that when if I have a positive and negative here and a positive and negative here, the directionality of them, when I bring them together, they'll be pulling this way, but they'll be pushing away from each other that way. If I change the directionality, now all four of them would try to come together because of the way we've got the little arrows drawn. But we just picked a direction and then use that as the convention. And positive and negative, the mathematical operators, were used. With magnets, probably because we were navigating long before we were doing a lot of other sophisticated math, and we figured out that you could take a magnetized object, float it in water, and it would align itself with the planet. Okay, I don't know how the flat earthers deal with that, but anyways, it would align itself with the planet. We also figured out that if you take a bunch of magnetic particles and lay it around the magnet, they'll form. They won't just scatter evenly. They'll actually form in little compressed, dense lines. Well, those are the physical lines of force. Well, that's representing the physical lines of force. And note that as you get closer to the magnet, it gets a lot denser. And as you get further out, the density gets less and less. Here, it's a little weak out in these areas. Out in here, it's got a whole lot of density down in there. So the density of these lines of flux also varies. And of course, with magnetism, likes repel, opposites attract. Same direction lines of flux repel, opposite direction lines of flux attract. And then we also use the vernacular instead of positive and negative, we use north and south, probably because that's what we had already labeled on the planet. Now, from my perspective, this makes things a whole lot easier because the lines of flux go from me emanating outwards to everywhere else, right? I have no problem remembering this. Lines of flux always go from me to everywhere else, right? I am the center of my universe, so positive to negative, north to south. That you're going to need to remember because that probably exists in FAA test questions. In truth, we could have drawn it the other way around, but that's what we chose to do. Here it shows a magnet affecting a bunch of little compasses. And you can see all the compasses going all the way around like this and then coming back around like a bunch of little tadpoles. Somebody invested in a whole lot of little compasses for that. So this part's really cool. Let me tell you, if this page wasn't true, life would suck. Okay, we wouldn't be sitting here or if we were sitting there, we'd all have little candles, we'd be huffing wax, right? There'd be no running water, no flush toilets, and most of the stuff we have wouldn't have been makeable, right? The fact that we can have electrons moving through matter to make magnetism is really useful. The fact that we can use magnetism and physical motion to make electricity or electrons move is also really useful. We can then take and build systems that will cause stuff to move, and that movement will then drive not only our magnet, but our wires, and it will cause electricity to happen. We can then run that electricity through conductive lines out to wherever we need it and use it to move things like pump the air conditioning, make light, pump the water pumps for the toilet and other running water. Okay? All the really, really cool conveniences of life. How many of you have lived without electricity? Kind of sucks. Let me tell you. It's one thing if you plan it. It's another thing entirely if you had no expectation it was coming. It's interesting that there are some materials that are very, very permeable, is the term, to magnetic action. And in fact, they will conduct magnetic lines of flux. So if I have some magnetic lines of flux, like I showed you in that one magnet, if I took that magnet and bent it around into a big horseshoe, if I bent it into a big horseshoe, took the magnet, made a big horseshoe out of it, now my lines of flux would be going like this and like this all the way around. But if I took a piece of iron and put it across there, all the lines of flux would jump into there and they'd be gone from out here. Okay, they'd snap right into there. And as a matter of fact, what would happen is, as I brought the piece of iron close, they'd all jump into it before I ever even made contact. They'd all jump right into it, and about in there, more and more would concentrate, and as soon as I made contact, they'd all finish concentrating in there. And I have very little magnetic lines of flux outside of that piece of iron. In fact, if I wanted to prevent those magnetic lines of flux from affecting anything nearby, one way to do that would be to put that piece of iron there. Okay, so that piece of iron is said to be permeable, which is conductive for magnetism. Okay, it's also very important to note that the relationship between that which is a good conductor isn't necessarily universal with that is a good flux conductor. So we could say that iron is a reasonable conductor of electricity, of electron flow. It's actually not that great. As metals go, it's okay. Actually has a fair amount of resistance in it. Copper is way better. So copper and silver are way, way better. Much better conduction of electricity with much less heat forming. Aluminum is even quite a bit better. In fact, aluminum is very good. So iron isn't that great, but it is wonderful for conducting, or for permeability, for conducting magnetic lines of flux. Does a great, great job. Same thing is true, a good insulator for electron flow, like nylon or Teflon or Kapton or other PFEs, even polyvinyl chloride. They're fairly good at stopping electrons from going where you don't want them to go as an insulator. Magnetism goes right through them. And very little effect on them. There are other materials you can use that will reduce the amount of magnetism that goes through, but okay. So this is where it starts to get a little weird. But one of the first things that we need to talk about is the forces we've been talking about with respect to gravitational force, electrostatic force, and magnetic force are highly dependent on proximity. So we've said how small an atom is, right? That 600 feet deep. Well, okay, that's pretty dinky, pretty really small. So the distance between the proton and the electron isn't that much. Okay, very small distance. If I take a bunch of atoms and lay them out in a small thin plate, and then throw a bunch of electrons on them, having pulled the electrons off of another bunch of atoms on another plate that are right next to each other, and if I keep them very close to each other, the static force will transmit across that other side. In fact, I might, if there's enough static force, the electrons might start hopping, and it'll cause an arc. But if I put something, an insulator, between them, I can create a lot of static force between those two plates. Once that thing's nice and charged up, I can then use it to do something. That's called a capacitor. I can use it to do a variety of different things. But if I separate those plates, the physical amount of force that the negatives and the positives are creating disappears quickly. And it's logarithmic. It's orders of magnitude. So if I go from 1 unit of distance to 2 units of distance, it's like exponentially, only cube exponentially reduced. Okay, the other thing is, anytime electrons move through matter, they will generate some heat. And that heat will be a loss of energy. So whatever caused the electrons to move will take some energy to cause the electrons to move. And a little bit of that energy will be lost in the form of warming up whatever the electrons are moving through. Whether it's moving through my body, moving through a conductor, moving through the telephone pole that was a few feet or about 30 feet away from me when the lightning bolt hit it. Okay, and it warmed up. The top 8 feet of it warmed up so quickly that it turned into toothpicks, and of course the concussion was pretty mighty. Any electrical travel will cause some heat and a little bit of loss of energy. Energy exists everywhere. There is any matter exists in some state of kinetic energy. It's sitting there vibrating around. Every molecule is sitting there vibrating around. The exception to that is those few molecules in space, probably in the center of a black hole, that there's so much density on top of them, they're not moving. And they exist at a state of absolute zero. Zero on the Kelvin scale, minus 273 on the Celsius scale, was it minus 459 in Fahrenheit, and 0 on the Rankine scale, something like that. So if I take everything down to the point that all molecular activity stops, motion stops, okay, not only does it become extremely conductive, any matter, extremely conductive, but there's no heat energy in it. We've taken all the heat energy out. So all matter exists in some state of energy, kinetic energy, in the form of heat. But there's also these packets of energy that one small portion of those packets we call light. But in truth, it's a really wide range of packets of energy. So the best way to describe this, I don't know if this is the best way, but it's the way I try to describe it, is if you take an energy source. So probably the most significant energy source anywhere nearby is this thing called the sun. That's sort of down that way somewhere. Kind of go that way a little bit, down there. Okay, it emits energy in all directions. All these packets of energy. So let's take a little chunk of those packets of energy. It's going out, filling space. All of space is filled with these packets of energy. Of course, the further out they go, the density of them is less and less. But they're still there. So let's take a little chunk, a little square ribbon of those chunks of energy, and let's imagine them as a river going by. They're going by at 186,000 miles per hour. Okay. Excuse me, 186,000 miles per second, or 300,000 meters per second. It's a fast river. Okay, but it's still a river, right? Now, if I reach over that river and I start going splash, 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 splash real fast, I'm going to get a ripple in that river. We have all those packets. And in fact, all the different packets could be rippling at different frequencies. And if I went faster and faster and faster, the ripple that I'm putting in, pretty soon everything would be moving so fast that your eye wouldn't be able to see it, right? Kind of like the propeller going so fast you can't see it anymore. So I could actually get a frequency that's way faster than your eye can see. I could also go the other way with this river and go really slow. In fact, it's so slow that I come up today and I'm looking at a low point in the wave. Come back tomorrow and I'm looking at a high point. So all I'd see is it looks like the river kind of went up and came down every different day. Of course, we really wouldn't see that in the true three-dimensional model, but that would be a very, very, very slow frequency, right? So in this case, the river or the packets of energy coming out emanate in wave form, even though they are little, can be treated as little particles of energy, or little packets of energy traveling along. Some of them operate with such a velocity and such a high frequency that matter can't stop them. Most of them, on the other hand, matter will interfere with their travel. It'll either, if it doesn't directly hit it, the gravitation will cause them to pucker and shift and move around. Otherwise, if it directly hits it, it's kind of like taking a tree and put it in the middle of our river, right? They'll try to go around it, or they'll just flat be stopped, right? We learned that a week ago, right? When the big chocolate donut went by us. You guys have seen all the memes, right? Okay, they had a little black chihuahua and a little white fluffy dog, and the little black chihuahua went by the fluffy dog, you know. Then they had a glazed donut, a chocolate donut, you know. Oh yeah, well, that's what happened, right? The moon got in the way, and most of that radiation coming from the sun was stopped. Now, until it got right there, it was coming around, it was pretty bright, and it didn't really get very dark until it got completely blocked. However, there was still some radiation, some of those packets emanating at a high enough frequency, high enough speed, we call them neutrinos or other types, where they just shot right through the moon. There is nothing in the moon solid enough to stop them. Of course, they shot right through us and the planet Earth as well. There's matter doesn't stop these super, super fast, super high frequency particles. But all the other energy packets running out, they're operating in different frequencies, and we can stick our hand out there and oscillate them and cause little waves to ripple across, even though they're whipping by at 186,000 miles per second. Okay, and it'll ripple upstream as well as rippling downstream. There's a little bit of Doppler effect, but it's in the distances that we deal with, it's not that big of a deal. That sort of help understand that. So light is both a packet and really any electromagnetic radiation. It's a packet of energy. It has electrostatic qualities and electromagnetic qualities. I can create a ripple with either two voltage sources, different voltage potentials, or a magnetic source. And really, if I use electrovoltage source causing current to go back and forth, I'm going to do both. I'm going to create an electrostatic ripple and an electromagnetic ripple, and they will emanate at right angles to each other. So when we get into antennas, I'll try to do a better job of sort of modeling that. But for the sake of this conversation, coming off from this light, there's a bunch of packets of light energy that we can see. There's also probably some other spectrum energy coming off in the form of infrared because it's hot. Now, if it's an incandescent light, there'd be a lot more infrared. These guys probably have a little bit of UV coming off of them, not too much. Okay, but remember, those are out in the vibration spectrum that we can't see. Doesn't mean the energy isn't there. And then it goes way, way up and way, way down. In fact, what we see in the form of light is a very, very, very small portion of the range of frequencies within this electromagnetic spectrum of energy. So really in space, it's not empty. It's either full of energy or it's full of matter and energy. And in fact, the physicist will tell you once you get into particles smaller than those particles, the subparticles of the subparticles of those particles, it turns out that they're probably made of energy too. So someday maybe they'll be able to take that energy and cause it to relocate somewhere else. I hope they don't actually do that. Transport would be kind of cool. It'd be cool to have lunch in Paris. However, it would put aviation on its ear. So, and I like airplanes more than having lunch in Paris. Okay, so I don't know how else to describe what's happening there with light, but hopefully that works for you. A couple of other things about matter as with respect to conductivity is, as I said earlier, remember if we supercool it to 0, it gets very conductive. Well, temperature affects matter's conductivity. Now, for all matter, if you take it to 0, it gets a lot more conductive. However, also for all matter, there'll be some temperature range where its behavior acts a little weird for a variety of different reasons. So within the temperature ranges that we typically operate in, carbon is one that works a little backwards. For most matter, the hotter you get it, the more resistance it has. Carbon, on the other hand, from some fairly cold temperature up to a fairly hot temperature, it has a negative coefficient. The hotter you get it, the less resistance it has. And there are a few others that have that negative coefficient. Most material, tungsten, a great example. Hotter you get it, the more the resistance it gets. That's a good thing, because when I take a tungsten wrench and throw it across the circuit, a whole lot of current's going to go through it, and it's going to get really, really hot and start emitting a whole bunch of light. And in fact, if I can get it in an atmosphere that there's no oxygen, one of these inert gases, and it's a very thin little coiled wire, it will emit a whole bunch of light. It's called an incandescent light bulb. Okay? Its resistance will have gone way, way up. So if I turn it on and measure, or if I don't turn it on and I measure with an ohm meter, it's going to have very low resistance because it's dead short right across. But if I take and run a bunch of current through it, it's going to get hot and emit a bunch of light. And suddenly now when I measure it, it'll have source voltage drop across it. And it'll have obviously have a bunch of resistance because the amount of current going through it isn't very much once it's heated up. Okay? I can measure that. That's called inrush current, by the way. I'll talk about it later. Almost every component out there has a certain amount of inrush current. It's usually higher than its ongoing operational current value. So anyways, all of these qualities and characteristics need to be accounted for when we design a system. So if we take an electron away from an atom, so in other words, an atom has one less electron for the number of protons it has, or we do the opposite and give it an extra electron, we call that an ion. Either way, it's an ion. It's a positive or a negative ion. So this happens. You want to know how to steal an electron? Yeah, I just stole a bunch of electrons. Okay. I can use friction. I can steal a bunch more. And a bunch more. I probably gave some back now. Okay. If I get a nice certain type of material like a plastic rug and I do like this and I get all, wow, I can steal all kinds of electrons. Then I can give them to the kitty, right? You know, pow. All right, so friction is one way I can steal a bunch of electrons. I can also create a chemical environment where as long as a chemical reaction is allowed to occur, there will be a voltage potential. And if I let current go, then electrons are going to travel through my circuit, and then chemically they'll travel through the chemical arrangement. So all I got to do is take two galvanically dissimilar metals and suspend them in an electrolyte. There'll be an ion exchange of charged atoms moving between the two dissimilar metals. One will be anodic, the other will be cathodic, and they'll start to one will corrode, and the electrolyte will start to change, may start to change state, depends, or both plates will change states. So chemically, we can get a bunch of electrons to move. Friction-wise, we can certainly get a bunch to move. And then of course, as I said earlier, we can use magnetism to get a bunch to move. It also turns out that if we take certain types of material and suspend it in glass or silica, take certain types of material, one atom at a time or one molecule at a time, and suspend them. So maybe every 300 silicon molecules, we'll put one of these little germanium molecules. Okay, and we'll just spread them all around in there. And then based upon the structure, as well as the mounting arrangement and all the rest of the stuff, some spectrum of those packets of energy might be in the infrared, might be very high up, might be in the visible light. They'll start striking that medium and eventually cause an electron to jump off, and another one to jump off, and another one to jump off, and they'll start moving through at a fairly slow rate. But if I put a bunch of these out there, I'll get a whole bunch of electrons moving. Call those the photocell. And if I have bazillions of them out there. In fact, it turns out that if I cover the state of Nevada with these things, I will produce more electricity than is currently being used than all of North America. And that's with today's technology. And the upside, who cares if we cover Nevada? Right? All the lizards are going, whoa, shade, this is pretty nice. So by today's technology, and this is one of the areas that technology is advancing rapidly, the relationship between light emitting because of electricity or electricity emitting because of light being received is in these diodes, is what they're called. It's what's happening in the world of the electromotive sources, the solar cells, is we're developing the technology such that it's being hit about with the same amount of light, but it's a much wider spectrum that can cause the electron movement. So right now, early on, it was just a very narrow spectrum on the high end of the visible light range. Well, now we've got them where it's all the way down deep into infrared and the other direction into ultraviolet. So all these different frequencies or bands of these energy packets, the solar cell can convert them into electricity. That's where we're going to see huge, huge changes. And it's already to the degree that it's economically feasible. They're huge fields. I don't know if you guys ever fly out over the desert at all, but there's huge, I mean, acres and acres and acres of these things being built up. And every time I fly, there'll be a whole nother area being converted. And right now, it's just dirt, nothing. I mean, it's Barstow. Okay? There ain't nothing there. Even the lizards don't like being there. Okay, the other thing about these electrons, as you might remember, they're going to travel through, and if you get them to go in an organized manner, they'll travel, and we're going to use units of ampere. We'll label it I because ampere doesn't have an I in it, so let's use I. I've read somewhere that it referred to intensity, which is why they used I. But anyways, it turns out a couple of points to make. First off, the electrons actually don't like just going through the metal, the conductor. They much prefer being on the outer edge of the conductor. They tend to travel through the surface. It's so much so that what happens is they're traveling along the surface and they're creating magnetic fields outwards and inwards. And so inside, the material on the inside has got all these eddy currents, which I'll talk about later. And that's actually interfering, causing the wire to heat up. It's causing a loss of energy. So anytime you really want a lot of electricity to flow, we actually don't make a wire, we make a tube. All the big high power lines you see coming out of San Onofre and all the power plants, those aren't wires, they're tubes. what they do is they take a bunch of, sort of like laminate flooring. They take a bunch of pieces of copper that are shaped like this, tongue and groove, like that, and they take a whole bunch of those, stick them all together in a tube, and then they twist it. That's what keeps them all locked together. Okay? And the super, super high voltage, 60, 70, 80, 90,000 volts. It all travels along in the surface of that tube. And the interior is completely empty. Right? Okay, so that's one thing. The other thing is, it doesn't go very fast. Well, we've said, wait a minute, it goes the speed of light. So you remember how many atoms there are per inch? Okay? I'm sure if you took the whole pin and made the ball the size of the grain of sand, you'd fill the whole solar system up. I mean, I don't know, there's some way of equating that, but there's a lot of atoms in an inch of wire. So, and I forget what the value is, but there's a value at 100 volts with XYZ resistance. It's, you know, electrons travel like 11 inches a second. It's very, very slow. If I throw an electron in at 186,000 miles per second, another electron will come out. But the actual electron hopping through the wire will only go 11 inches at some voltage, at some amperage, with some resistance. So, because it's doing so many individual hops. All right. And also, remember, we've been talking all along about force. Physical pushing or pulling. In the world of kinetic energy, we've already got all this laid out. We've defined power as the capacity to do some measure of work over a period of time. So work divided by time. We've also defined work as force over some distance. So I apply a force. Once it starts to move, distance comes into it, and then the amount of time it takes that to happen defines the power being produced. We can also do the same thing with electricity by using various different units of force and distance and time. Although with respect to distance, we're going to sort of mix the two together. What we're going to do is we're going to define distance and time in one term. We're going to call it amperage. That I think. We're going to say some quantity of electrons or coulomb of electrons traveling by a given point in a second equals 1 amp. Well, that gives you your distance and time, and then the voltage is the force, all thrown into that formula. So the exact same formulas you guys probably played around with a little bit in general apply here. Okay. So also you will remember that the force that exists between two electrically charged components, and every component is technically electrically charged. The force that exists between them is measured as voltage. It doesn't necessarily have to be working. I can have my two poles. One could be at a minus 10 volts, and the other could be at a plus 10 volts. I have 20 volt potential between the two. But as long as no electricity is traveling, it's just a force, right? No work's happening. Just like I'm pushing on the wall, as long as the wall doesn't start to move and I don't start moving the other direction, okay, no work is actually happening. Okay, how much electrons will flow always depends on the amount of potential between the two sources and the conductivity of the material between them, which can be nothing, hard to measure in outer space because there's no matter. It can still do it though because of those packets of energy. The bolt can occur. It a lot harder for it to occur in complete space. Where it actually occurs the easiest is when you have a very small amount of gaseous matter. Okay, then the voltages, the electrons love to jump from one to another, which for us in airplanes is a little bit of a problem because we have to go way up high where there isn't much matter. Pressure is really, really low. Electrons really have a hard time with high pressure traveling through non-conductive materials like air. Again, so because all matter has some resistance to electron flow, not only does the temperature affect it, but the length of the circuit affects it, and the cross-sectional area of the circuit affects it. Now, it's a little hard to think about it in a singular manner, though. Even if the cross-sectional area is really, really small, it'll conduct a whole lot of current. The problem is it'll heat up so fast that it'll melt itself very, very quickly and thus stop conducting current. But for a very short period of time, even high resistance, if you get enough voltage potential, even a high resistant material will conduct. It'll just heat up very, very quickly. So it's really important to say, even with a small wire, it can conduct a lot of current, it just will melt. So part of the question here is, it's got to have enough cross-sectional area to have enough surface area to expel the heat that develops in it and not go molten on you or not burn the insulation off. Okay? So if I make the conductor smaller, it's going to have a higher resistance, therefore it's going to get hotter, and it may go into meltdown. So cross-sectional area is somewhat of an issue. If I have a low cross-sectional area, but I cool it, suspend it in a liquid coolant, then it's not an issue, right? This is sort of the same problem we have with internal combustion engines. Man, I could produce all the power in the world. I could make an engine produce 10 million horsepower. The problem is, after about a quarter of a revolution at producing that kind of power, it'd get really, really hot, overheat, and melt stuff, or actually start bending stuff, one or the other. So the limitation on many of these power systems is really more its ability to reject heat, right? With the internal combustion engine, it's kind of difficult rejecting heat. With a big copper wire getting 3,000 amps of current run through it, it can be a little difficult to reject heat. Particularly if we insulated it with a bunch of electrical insulator, which is also a little bit of a thermal insulator. Okay, we put a blanket around it. So we call this resistance to electron flow R, although the units of measure are ohms, even though there's no O in R or resistance, or omega, or an H, or an M. There's an S though. Are you confused? I mean, what it was is they had all these guys that invented something. They had to give them a name for it, give them some credit. So there must be some agency, you know, like one of those secret Galileo agencies. That's the agency that picks who got credit for what, right? And of course, there was a lot of cases where different individuals invented the same thing in different places. So this here pretty well lays it out. Power equals force times distance times time, or divided by time. We can say the same thing. Voltage is the force. Amps is the coulombs per unit of time. So coulombs equates to the distance because it's the number of units, the number of electrons strung out in a circuit moving by a second. So that's a quantification of distance. We will then express that in units of watts, which, well, there is a Debian power, so that's sort of got something, right? We unfortunately had some other guy, a group of guys came along, and they went all around the world and they measured every horse. They got behind the horse and they hung on. They must have had a big like wagon full of beer. Okay, and they measured the amount of pull that the horses all have, and they came up with some average and said, okay, that's the average amount of oomph a horse can pull. So we're gonna call that a horsepower. Well, once they then figured that out, they had to go back and say, okay, well, some way of equating these two different expressions of power. So they essentially said 1 horsepower of kinetic energy equals 746 watts of electrical energy, or power. I can say power. Okay, that's just the magic number they came up with. You know, they did a whole lot of science and research to establish that. The reason it's an awkward number is because at the end of the day, what did they start all of this with? Huh? Well, on one end they started with a horse. On the other end they started with a coulomb, which is a nice round number, 6.28 times 10 to the 26. That's a nice round number, right? A lot of zeros. They're round. Yeah. So ultimately, 746 is what they ended up with. Where they came up with what an actual horsepower is, I'm sure we could look it up, and there's some British measuring system. They've got a Clydesdale or a Shetland pony or something out there that they used, and then once they came up with that value, they came up with some mechanical system for equating to it. Across the little river there between England and France, over into Europe, they came up with the System International, or the metric system. They got a kind of different way of doing it, but it's still an expression of power, and it's what is it? Newton meters. Saying that right? I think yeah, Newton meters. Okay, and we all remember Ohm's law. Okay. It's important to note that we can design all this stuff so the electrons go where we want them to go. And every once in a while we blow it and they don't go where we want them to go. They either don't go at all, they go somewhere else, or the little thing that's inspiring them to go stops working. So remember, as I said, very slow rate of travel through the conductor. But if I use the metaphor of the pool balls, I smack the ball here, the energy travels at the speed of light, smacking the other one out. So an electron comes in, smack, another one smacks out. So it is important for you to be able to call it a circuit. And I know some of you, because I've seen some of your drawings. For you to be able to call it a circuit, it's got to have an electromotive source. Either a battery, a generator of some type, me walking across the floor, scraping electrons off the carpet. Somewhere or another, it's got to have an electromotive source. It's got to have something that will conduct at the voltage I'm operating at. Now, if I'm God and I've got a bunch of clouds and I'm rubbing them all around, I'm the weather god over Houston, and I'm rubbing them all around, I can collect a whole bunch of electrons. I don't need much of a conductor. I can pretty much conduct anything I want. Air, humans, mountains, trees, whatever I want. I can get millions and millions of volts, kapow, 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 and fire that electricity any which way I want. For the rest of us mere mortals, we're probably going to need something that's made out of metal. Most metals are okay conductors relative to everything else. Water, unfortunately, is a pretty good conductor as well. And guess what we're made out of? I think what's the average human weigh? About 10 pounds if you take all the water out? 12 pounds something? Okay, 30 pounds. Right? So, yeah, we're pretty conductive as things go. How much voltage does it take to electrocute yourself? 100 volts?
Isn't it the Amper?
Huh? Well, I just said electrocute stuff. To get a good shot, to get electrons zipping through you.
Well, 120 is enough.
120 is certainly enough, yeah? How about 100?
I was gonna say 9 volt.
There's a video on.
A 9 volt? Oh, how do you feel a 9 volt?
On your tongue.
Make the conductor really good. Put a little water there, right? A little spit, all right? You'll feel it. So 9 volts pretty good.
Yeah.
Let me tell you, I nailed myself 12 volts. Working on the car, the battery's there, it didn't have a rag, leaning out like that, put a lot of pressure in the grease, and all of a sudden my arm was smoking. I mean, just, I burned myself both sides, it just Zappo. So 12 volts can definitely do it. 6 volts can do it. It's really a function of how good of a connection you make. I'll tell you, if you take a wire and stick it in your vein, a wire, stick it in your vein, hook it up to a 1.5 volt battery, you probably would feel it. You got a good enough conductor. Okay. It doesn't take a lot. Now, to mess with your neurological system to the degree that your heart stops or something along those lines, it's probably going to take a little bit of current to do that. However, contrary to what Hollywood would have you believe, your body isn't as conductive as straight water is. So I don't recommend trying this because every once in a while electricity does something weird. But the notion that the damsel in distress was murdered because they threw the toaster oven in the bathtub while she was standing or sitting in the bathtub. I'm sorry, the electricity and the wires of the toaster oven are going to take the shortest possible path to ground, which will probably be the plumbing fitting in the bottom of the bathtub. The only way the sweet little damsel could have gotten electrocuted is if she opened the toaster oven, reached in, grabbed that red hot electrode in there with her foot sitting on the plumbing outlet of the tub. Okay?
Well, you didn't hear about that teenage girl that she took a picture of Instagram saying, "See, I can add a cable to my phone," and she got electrocuted right there. But the picture went right on Instagram.
She did. I didn't hear the part of she did what?
She was taking a picture on Instagram. See, I can plug my phone in while taking a bath. And then they got on Instagram, and then her parents found her dead in the bathtub.
Well, what she probably was doing was exactly that. She grabbed the toaster oven. So there's some part of the phone that had a conductive path.
Or the wire was broken.
The wire, like I say, one side of the wire was broken, and one part of the phone wasn't shielded like it's supposed to be. So she actually she grabbed the wire inside the toaster oven.
A lot of people have exposed in their phone chargers that they never take care of. A lot of people have exposed wires from their phone chargers.
Right.
They
That
just
could
don't
also
sit
be
there.
it. The other part of it that's interesting is, I don't know where she was, but if she was in the United States, she should not have been able to get electrocuted because the law says you cannot have a receptacle in a bathtub, in a bathroom area that doesn't have a ground fault interrupter. That can immediately sense electricity is doing something wrong and pop the circuit breaker.
I don't know.
Well, yeah, so she may not have been in the U.S. Or is in a house that is not legally put together. That's the other part of it that, like I say, I lose it on some of these Hollywood things where, like, okay, yeah, that's not possible. Okay, so you got to have a conductor. You got to have a load. If you don't have a load, one of the conductors will become your load. Okay, so if I just take a conductor, my wrench, and put it across the battery, it's going to become the load. It's going to get really, really hot, right? Okay, so you need a load in there. Of course, the whole purpose of doing this is the load. Make the motor, make the light, make the toast, make the whatever, right? It is optional to have a controller. It's very convenient, but it's not mandatory for it to be a circuit. Okay, you can just disconnect the battery every time you want to shut the car off. Sure. I've been poor enough where my Volkswagen, okay, so I sort of hot wired it. But anyways, but yeah, most of the time it's pretty convenient to have a switch, a controller of some kind, whether it's a computer doing the controlling or a manual human interface device. You kind of need it, but it's not mandatory. So these pictures, there's the cooling towers for probably a nuclear reactor, although that could be a Kohlberger. Here it looks like we've got a bunch of battery banks. There's some solar and wind going on. This is probably a big hydroelectric, so they run water in, superheat it to super high pressure steam, and then feed it through this big huge turbine assembly and extract, and then use that to drive the shaft of a big generator. I don't know how many millions of watts. Look at the size of these bolts. Oh, dang, those are some big bolts. Must be one big wrench. Okay. So the other thing is, it turns out that most devices, most loads, they don't care which way the electricity's going. Electricity can be going this way, or it can be going back and forth, back and forth, back and forth. As long as it's doing something, the toaster doesn't care. The microwave doesn't care, the light bulb doesn't care. Most devices don't care. In fact, it turns out the only thing that really does care is a chemical source, a battery, and then these little digital circuits we've been talking about. They care. Other than that, it's very, very convenient to have alternating current. You can step voltage up, current up, down. You can do all kinds of cool stuff with alternating current that you can't do with direct current. So it's way more advantageous to have alternating current. So for most devices, we use alternating current as much as we can, and then convert a little bit of it to digital or to DC, direct current, for where we need it, for charging the battery or for running a little digital circuit. So, for example, the microwave oven. The big oven, the little motor spins around, all that's all AC. The only part that's DC is the little computer control with the little digital clock, right? And the little push buttons. So we'll have a small little rectifier that converts the AC to DC, and a little power regulator because you need to drop the voltage way down. And that will run the controls, and the controls will then run relays, DC relays, that then turn on the AC to the microwave tube, to the little motor, to whatever else is in there. Okay? That's also true in your laptops. Okay? Power supply comes in, it sends a bunch of AC out to the backlight, to several other components within there, and then converts the rest of it into DC for all the digital parts of the circuit. Toaster doesn't need it. Well, you can't have a toaster that doesn't have digital, right? What good is it? Well, my wife told me the other day, we need a new toaster.
So it's going back and forth, alternating current. Is it voltage, is that what's still driving it forward? If it's still
No,
driving-
the voltage, when we get into power generation, you'll see why it goes back and forth. But we're literally taking the voltage source and going this way, that way, that way, that way, that way, back and forth. Because of the way we generate power. We get into power generation, and the next set of slides, it'll begin to make sense. Because it's doing that, because of inductive coupling, we can use that magic thing called the transformer to exchange voltage for current or current for voltage. That's really, really handy. And we'll talk about why it's very advantageous to sometimes have very high current or have very high voltage. The downside of this is if I'm tubing along like this, and eventually I'm going to turn around. So I turn around and I'm going like this, and I'm doodling along like this, and I'm going to turn around. I'm going to turn around and go this way. What has to happen?
Changing momentum.
What's going to happen every time I change direction?
Loss of energy.
At some point, I'm going to have to be what's called stopped.
Yeah.
Okay. So if I turn around once every couple of seconds, the light's going to go out. Okay, so if the light went out every couple of seconds, how long do you think it'd be before you get nauseous, have a headache, and throw up? Okay, flick, 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 flick. Okay, that'd drive you nuts pretty darn quickly. Well, it turns out that up through about 15 to 20 times a second, most human beings will get a headache, they'll get nauseous, they'll have all kinds of problems. There are some human beings that up and around to about 30, 35, maybe even as high as 40, can have medical medical issues. Typically, not above 40. That's why most of the world is at 50 cycles per second, or 150 or 100 times on off. It goes out 100 times per second. And in the United States, we're 60. We probably went 60. Well, A, we invented it, so we get to do whatever we want. B, we went 60 because it's a clean division of 3, and we were doing everything in units of 3. When we get into power generation, you'll see why we were. So it was logical. Now, make no mistake, the issues with alternating current were hotly politically contested. Hotly politically contested. This very, very nasty human being by the name of Thomas Edison. I'm not kidding you not. He was a hugely nasty human being. There are more child labor laws in the United States because of Thomas Edison than any other human being on the planet. However, it took that kind of an egomaniac to cause electricity to go to every building in America. And he was a living force. He believed that DC was the way to go. General Electric and those guys are like, oh, no, AC is way safer. Way safer. So they ended up in this big, huge contest saying, oh, this is safe, it's going to kill you. This one's way more dangerous, blah, blah, blah. Well, it turns out actually, literally, DC is far more dangerous than AC. That's why they use DC to electrocute people to death in the electrocution chamber. Okay? But it was a very hotly contested, and because it's so much easier to make alternating current, it economically became, it was going to happen one way or another. It's just so much easier to make it. And we really didn't get too much back into DC until we started building things that needed batteries, like automobiles. And even then, we used fairly small power generation, but the bulk of electricity was all AC. Digital has expanded that a little bit, but all right, this is a good place to stop. I was going to do a little bit of a math problem, but I think we'll do it next week. So let's break here, and then we're going to go back into lab. I'll get the cabinets open, so take about a 10-minute break or whatever you need to get the cabinets open.